So we're going to be looking at our first introduction to molecular orbitals now, and that's going to have to we're going to have to further our understanding of what we mean by an electron first of all. So we've seen this symbol here, which is psi, which represents the wave function for an electron, and that wave function allows us to describe a shape. We've seen for a 1s orbital that could represent the shape of that orbital. In the middle we've got a nucleus, and then this region of space here is a region where we have a 99.9% probability of finding the electron. It could be anywhere within here, so we think of this as basically being a probability density. And don't forget that we can get two electrons in here. We can get one with spin up or magnetic spin of +1/2 or -1/2. But also we've seen that electrons can behave as waves, and this is really quite a hard idea to visualize and conceptualize, because in fact both of these ideas are two extremes, and the reality is probably something halfway between. So if we could sort of imagine, and it's quite hard to draw this, a wave moving around the edge of that 1s orbital, and that becomes really important, the idea that it can exist as a wave, as well as this particle and the probability density, because when we think about waves, then we can have a positive displacement here, so that's the maximum positive displacement, which would be the amplitude, and then we can have a negative displacement. So if here's our zero line, our wave is moving to its maximum positive displacement down to its maximum negative displacement, and that gives rise to the idea of wave addition and wave subtraction, and this is really important in molecular orbitals. So if we were to have, for example, two waves, so we're adding these two waves together, where we've got positive displacement, and they are coincident here, they're occurring in the same place. So if we added these two waves together, what we'd end up with is a wave that had twice the amplitude, twice the positive displacement of the original one, because we've added these two together. So then if we think about what could happen if we had this wave adding to this wave, then what would happen here is the waves would cancel each other out. And we say that these two waves are in phase, they are exactly in phase, and these two waves are exactly out of phase waves. So the sorry, I just realised that should be a negative there and a positive there. So this and this have cancelled each other out, and this have cancelled each other out. It's ideas like this that actually leads to a wave interference, that sort of feature you sometimes get when you're driving along in a car and listening particularly to AM radio, where you get the radio coming into phase, so it gets louder, and then different waves are interacting with each other, and then it's getting quieter. So if we just think about what we've done there, we've really taken the idea that an orbital can either be thought of as a region of space where we could find an electron, so there is a particle, in this case two particles, somewhere in this region of space. Then we also need to think about it existing as a wave. Neither of these probably reflect actually what the reality is, but we need to think of them like that. So let's have a look at our first type of bond, and we're going to have a look at, I'm actually going to start with a p orbital to start with, because they're a little bit easier to understand. Okay, so if we have two p orbitals, and these in this case this would be the two px orbitals, and I'm going to label this as plus and this is minus. This is not charge under any circumstances. This is just saying that the wave here is in the positive part of the displacement, and the wave, electron wave on this side, is in the negative part of the displacement. So because both of these are going to interact and they are in phase, what happens is, as the nuclei come together, we end up with the waves or the orbitals adding together. And when we have two electrons in here, that now means there is electron density in between these two nuclei. So because we've had these in-phase electron waves adding together, we end up with a new probability area in between our nuclei, which is where the wave functions have added together. And we call this a molecular orbital, because it's not now single atomic orbitals, they've added together and we get that. But we've also got the possibility of waves arriving together out of phase. And exactly what happened with our waves earlier, when these come together, then they cancel out. That positive and that negative displacement cancel out. And we have here an anti-bonding molecular orbital. So there is no electron density and no probability of finding an electron between the nuclei here. So plus, minus, minus, plus. The same thing can happen with s orbitals. It's just a little bit harder for us to conceptualize, because we haven't got two lobes to deal with now. We've basically just got one spherical region of space. So it could be that the wave function that was the wave that was describing this electron happens to be for that moment in time in the positive displacement, and this one happens to be in the positive displacement, and then we add these together and we get a new molecular orbital here, where here are our nuclei and there is a probability of electron density in here. So this is a bonding molecular orbital. The same thing can happen as happened with our p orbitals. So it happens to be that at this part of the wave, this is in the positive displacement, this is in the negative displacement, and they cancel each other out. So again, this is called an anti-bonding molecular orbital. So both of those orbitals that we have seen can be formed by a s orbital. So 2 times s orbitals can provide a sigma molecular orbital. We call that, in this case, that would be a sigma s molecular orbital because it's made out of s orbitals. But we can also have what's called a sigma star, and that's the anti-bonding orbital. So that's a sigma to show the type of molecular orbital that's been formed, and the s to show that it's from the s, and then that star there shows us that it's the anti-bonding orbital where the waves have arrived out of phase. We can get 2 times px orbitals, and that's important because you actually get a different type of bond formed with py and pz orbitals, but we'll talk about that in a future video. So 2 times px orbitals, and that will give us a sigma p and a sigma p star, or sigma anti-bonding orbital. So what does this actually mean in terms of bonding? Well, now we're moving away from our Lewis structure, so electrons as dots and crosses, and thinking about what actually happens when these things form. So we're going to look at 2 examples, and then you can have a go at doing 2 examples yourself. So we're going to have a look first of all simply at the H2 plus molecule. So this is a molecule where we've got 2 hydrogen atoms and we're down or we're short of 1 electron. So we've got our 1s orbitals, and these are the 1s orbitals in the unbonded hydrogens. We've got a electron in there, and obviously there's no electron in here because it's a plus ion. So what can happen is we form a new, when these two bond together, we form a new sigma s or sigma 1s in this case bonding orbital, but there will also be a sigma 1s anti-bonding orbital, sigma 1s star, to show that's anti-bonding. So the electrons, when they move into the molecular orbitals, are always going to occupy the lowest energy state first. So this electron is going to go into this orbital here. So what that then means is that this is a feasible molecule, and we have 1 electron in our bonding orbital. So if we actually think about doing this diagrammatically earlier, here's our 1s, that's got an electron in it. So when it forms the molecular orbital, so these would both have to be in phase for this, to form this molecular orbital. We've now got 1 electron somewhere between those nuclei. And we can also think about something called the bond order here. And the bond order is going to be equal to the bonding electrons minus the non-bonding electrons divided by 2. But we're actually going to come on to that okay. So in this case our bond order will be bonding electrons, there's 1, there's nothing in the anti-bonding orbital, so our bond order would be a half in this case. So let's have a look at the H2 molecule now. And it might be that if I start this up, you want to pause the video and actually have a go yourself. So H2, we start first of all with our 1s orbitals. 1s orbital, that's got 1 electron in for a hydrogen atom, and that's another one. So this is the 1s orbital for the each hydrogen atom. When these combine in phase, we get the sigma s bonding orbital, and when they combine out of phase, we get the sigma 1s star anti-bonding orbital. The electrons fill up first of all in the lower lowest energy orbital, so they're both going to move into the sigma 1s orbital. So this is a molecular molecular orbital bonding diagram for H2. So if we think about the bond order, and that's going to be bonding electrons, which is 1, 2, minus non-bonding electrons, which is 0, over 2, so the bond order here is 1. Let's look at our third example. So this is a theoretical ion, and this is the He2 plus ion. So we plot the energy. First of all, we've got our 1s orbitals. He2, so each helium atom has got 2 electrons, but there's 1 electron missing because of the positive charge, so one of them is only going to have 1 bonding 1 electron. So when these two orbitals come in phase, we get the sigma 1s bonding orbital, and when they're out of phase, we get the sigma 1s star antibonding orbital. We've got 3 electrons to put into our molecular orbitals now. We put them first in the lowest state, so the lowest energy level, and then the third one goes in there. So looking at our bond order again, 2 bonding electrons minus 1 non-bonding electron divided by 2, which is therefore going to be equal to a bond order of a half. Our final molecule theoretical because it can't actually exist, and you'll see why in a minute it can't exist. So here at He2, each helium atom has got 2 electrons, so 1s, we put 2 in each of them. When these orbitals combine in phase, we get the sigma 1s bonding orbital, and then when they combine out of phase, we get the sigma 1s star antibonding orbital. We've got 4 electrons to go in, 1, 2, 3, 4. So because we've started to put electrons into the antibonding orbitals, that cancels out the bonding effect of these. So if we actually have a look at our bond order calculation for this, 2 minus 2 over 2, which means that the bond order is 0, which means that it's an unstable ion and can't actually unstable molecule and can't actually exist. In the next session, we'll actually start to look at the period 2 elements, and we'll therefore start having a look at pi bonds.